All right, so today what we're going to do is we're going to review and reinforce your knowledge about probability trees. Now, probability trees are simply a way of organizing what are called compound probabilities. Okay? Compound probabilities because you have more than one probability happening at the same time. Now, so before we start that, I want to hopefully remind you, of two really important words in probability. And each one of them has a rule. The first one is the AND rule. Anytime you're trying to find the probability of two events, and it's connected by the word AND, the AND rule says that you just take the two probabilities and multiply them together. So, the probability of A and B is the same as the probability of A times the probability of B. And that's one of the reasons that probability trees work so well. As you're going along a branch in a probability tree, it's this probability and this probability and this probability, right? So it's very easy to organize those rules. There's also something called the OR rule. Now, the OR rule says that the probability of A or B can be found by simply adding those probabilities together. So the probability of A plus the probability of B. Now, this one can get a little more complicated when you have when the events are not mutually exclusive, but we're not going to worry about that right now because probability tree statements are always exclusive, right? You can follow a branch to only one direction. So we're not worried about it so much yet, but we'll talk about it a little bit later. Okay? So keep in mind, if you see AND, what operation? Multiply. If you see OR, what operation? Add. There you go. Good. All right. For a probability tree, you have a basic structure. A probability tree is designed to help you create a visual representation of probabilities when you have multiple events. Remember, an event is when you do something. And all probabilities have a start. Now, the textbooks here don't typically make you write the word start. I learned it with start, and I like it. Simply because if you think about writing something down at the very beginning, it makes you slow down, and it helps recall the material you need. So you don't have to write the word start, but I'm telling you, it's a great device to kind of help you get to where you need to go, right? So give it a shot. You might like it. Then you're going to have events. And so you have your first event and your second event. You're going to be doing different things or doing the same thing over and over and over again. Doesn't matter. You could have a third event, fourth event. They get huge very quickly, though. So be careful. Now, so let's say the first event, let's do one for flipping a coin. So if you're flipping a coin, we're going to flip a coin twice in this instance. We can either get a heads or a what? Tails. Notice how nicely spaced apart they are. And the reason for that is because they're going to branch again for the second time. If you get a heads on the first coin and you flip the second coin, what can you get? Heads or a tails. So they branch again. If you got the tails the first time, on the second coin you can get another heads or another tails. Right? So very straightforward. Try to keep it that way. Don't get too creative. Now we will have some trees that don't branch all the way. And we'll talk about that as we go. So say, for example, you're doing some kind of sporting event. And if you win the best 2 out of 3, the event's over, right? So if you win twice, do you then have to play the third game? No. But if you lose, then win, do you then have to play the third game? Yes. So you'll see some trees that don't continue to branch equally the whole way. Now, another thing that you need to remember or recall about these is that you're going to have a probability on each branch. Now, don't put P. I'm just doing that for effect. You're going to have an actual number. Remember that probability can be done in 3 different ways. You can have probability as a fraction, As a decimal or as a what? Percentage. Good. And usually here you're going to see a fraction or a decimal. The rule is, if it's a fraction that can be turned into a decimal without rounding, use the decimal. They're easier to work with, even on your calculator, right? But if it's a fraction that cannot be rounded nicely, or that has to be rounded, period, actually, then just use the fraction. Remember, your calculator can do all the math with the fractions, so it's not like it's going to be any big deal to you. Now, at the end, when you get your final answer at the very, 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 very end of the thing, we like it to be a decimal rounded to what? 4 decimal places. But do not round until you get to your final answer. Otherwise, you're going to introduce rounding errors the whole time, and your numbers are always going to be slightly off. Okay? And we'd have to count off for that. You need to remember, if you don't, that the probabilities on each branch, each set of branches, always have to add to 1. So, the probability of getting a heads is 1 out of 2. If you'll remember, the probability of getting a tails is 1 out of 2. And 1/2 and 1/2 combine to make what? 1. Okay? And many times you're going to be given some of the probabilities and you have to figure out the rest. So in this case, if I was only given 1/2 here, I know that these 2 branches have to add up to make a what? 1, right? So 1/2, the only way to make 1 out of 1/2 is to add another 1/2. So you may just, if you subtract from 1, it'll give you the other branch. Okay? Now in this case, I've chosen an example where they're all the same because flipping a coin is always going to be 1/2. Yeah? Yes?
What do you call like that?
The whole thing all the way up and down?
Yeah.
Okay?
But just like one bit.
Yeah. Well, I don't really know a name of it. What I do is I call this a set of branches because they all go together, so they kind of form a set, right? So this is a set of branches. This is a set of branches. Yeah? You're the first person who's ever asked me that. That's excellent. And I don't know. There's probably a word for it, but I'll have to find out. We'll look it up. But each time you have branches, that makes up a set of branches. And that set has to add up to make a probability of 1. Now notice, if you added all 4 of these, you'd get 2. That's because the branches need to stay separate. They don't represent the same probabilities. Okay? Now, another thing that you need to get used to doing that you're going to hate is at the end of each branch, you should label you should write the right probability statement, and you should do the probability for every branch. If you get in the habit of doing it, and then of course you're going to have some questions on where you're going to form a tree, they want it all. Okay? So be careful. So let's follow some branches. Let's say I take this branch to heads, and then this one to heads. I pass through a heads, and then another heads. So that's the probability of 2 heads. Or you could write heads and heads, or just H, H. It really doesn't matter how you abbreviate it, just write it. And if you look at that across there, this probability is 1/2, this probability is 1/2, and 1/2 times 1/2 is 1/4. So do you see what I've done? I've written the statement and I've written the probability. And you need to do that on all of them. So here we're going to go heads and then down to tails. So this is a probability of heads, then a tails. And because the probabilities are all 1/2, it's always going to be 1/4 all the way across, right? Here we're going tails, then heads. So that's the probability of tails, then heads. Again, 1/4. And the probability of tails, then tails. So 2 tails, again, 1/4. Again, this was a very simple one to draw and to work out the probabilities because the probabilities were all the same. But as you're traveling along branches, that's the same as saying and, which implies that you're going to multiply along the branch. Okay? Now, notice that this one says heads and tails, and this one says tails and heads. Unless they tell you that the order matters, the order does not matter. So what is the probability of getting a tails and a heads? Well, I can get a heads and a tails and a head, right? Because I didn't say that I must have the tails first, right? which means that I have to take these two and do what with them? It's either, because it's either that one or that one, so you add. So as you follow branches, that's always and, which means multiply. But if you get more than one branch that will work, then that means add, because those are ors. This branch or this branch would work, so it's an or situation. Okay, so you'd add them. Now, again, your only probability problem here is going to be when you have different probabilities along the branches and you have to figure out which ones. And then, of course, some of those where the branches don't go all the way to the end. Okay? All right? So let's go to the book and look at some examples. So here we go. In your book, page 19, where they're talking about probability trees. And we're just going to look at an example, then we're going to go do an example together, then I'm going to set you loose. All right? So, Angus had a bag of lollies. It contains 6 red ones and 4 green ones. Without looking, he selected a lolly and ate it. Okay, this brings up something. Then he selected a second lolly and ate it. What's the probability that he ate 2 red ones? So we're going to draw a tree for this. Now, remember, in the beginning, he had 6 red ones and 4 green ones. Yes? So, how many? Remember, we always have to have every possible outcome, because probability of an event is successes over total number of outcomes. Yes? So, if he had 6 red ones and 4 green ones, when he reached into the bag, how many total were there? 10. And how many of those originally were red?
6.
So 6 out of 10. Which means 4 out of 10 here. And those would easily change to decimals, because if it's tenths, 6 tenths is literally 0.6. 4 tenths is 4 tenths. Right? If you just name the fraction with a 10 at the bottom, we like the tens. So you could change them to decimals. You could leave them as fractions, but if you're going to leave them as fractions, you should do what with them? Simplify them. There you go. Simplify them. Yeah. So maybe reduce them. Yeah. Whatever word you use, it's fine. Now, okay, so he reaches into the bag and he pulls out a candy. But what did they say he does with that candy? He eats it. Which tells me that when he reaches back in the bag, he has fewer candies. Right? So this one is going to be a little more complicated to fill out. So let's say that he reached into the bag and he pulled out a red candy. Right? Well, that's not only reduced how many candies there are in the bag, it's also reduced the number of what? Red ones. So the probability of getting a red one has gone down by 1, as has the number of candies there are in the bag. Right? Now, if he got a... Okay, so we got our probabilities for each branch. Right? Here we go. And they didn't bother to reduce the fractions, but it doesn't matter. Remember, each set of branches has to add to 1. Right. So they're just drawing it. Check to make sure that the probabilities for every branch add to 1. So they're just calling that a branch. I think it's a set of branches because there's more than one. List the outcomes at the ends of each branch. So you see the probability of red, then they multiplied them, then they reduced it. They turned it into repeating decimals at the end. I hate that. And it will affect your numbers at the end, because the only way you can add with that is to use the rounded form, and that can change your answers. So I would use the fraction, just simplify the fraction, and don't do the decimal until the answer. Okay? But these will all add up to 1, except for the fact that they sometimes won't if you round them. So be careful. Okay? So, again, they mentioned the and rule and or rule. So the probability of 2 reds is 0.13 or 1/3, right? That's what we got. Okay. So, here we go. This one's very similar. Chris had a bag of lollies. He had 5 yellow ones and 3 blue ones. Without looking, he selected a lolly, then put it back in the bag. Okay. Clearly, Chris has mental issues that we won't go into right now. He then selected a second lolly. So this time, is the bottom number ever going to change from one probability to the next? No, because he's putting it back. just in this so they can see the difference. Doesn't make any sense. So now, remember from fractions that if this one's so remember that these two have to add up to 1. So if that top one is 5/8, 1 as 8s is 8/8, right? So I need 3 more of them, so 3/8. Don't make it harder than it has to be. But you could also put 1 minus 5/8 in your calculator, and it'll spit it out for you in reduced form if you need it. Okay, so here we still have 5/8, so that makes this 3/8. If this one's 3/8, that makes this one 5/8. And again, this is one of those probabilities that where most things are the same. Notice at the end, they're doing exactly what I told you to do. They give you a probability statement. Be careful. Probability statements, if you leave these off, your answer is wrong. And the grader will count them wrong, so be careful. Probability of yellow than blue, that's 5/8 times, it's there and there, so 3/8. Okay, 5/8 and 3/8, nothing will simplify, so it's just 15 over 64. And I just leave it as 15 over 64. You could change it to a decimal if you want to, but if you do, you're going to get rounding errors sometimes. Now, then blue, then yellow. Don't have to worry about doing the math. Why?
Is that the same as one above?
You bet. Now, that's not always true, but sometimes, but many times. And then on the bottom, 3/8 and 3/8. Nothing will simplify, so it's 9 over 64. Now notice how if they don't simplify, then you get the same denominator all the way down, and so it makes it really easy to check if they all add to 1, if they have a common denominator. But you don't have to do that. If it does simplify, you can simplify. Okay? So many times they're going to give you probabilities where you have to fill in the blanks in the tree. Now, from our probabilities, now you have that written down, I do not. What is the probability they selected 2 yellow ones? Well, to get to 2 yellow ones, there's only one branch that satisfies that condition. You have to get a yellow, then another yellow, right? So you're just following that branch, and there it is, and rounded to 4 decimal places, it's 0.3906. And I do want it rounded to 4 decimal places there because it's my final answer. Yes? Fractions to do the work, 4 decimal places to your final answer. Okay? So what's the probability selected? 1 of each color. So 1 of each color means yellow then a blue, or a blue then a what? Yellow. So what was the probability for yellow and blue up there? 15 over 64. And the other probability was also 15 over 64. So I have 2 branches that work this time. Either this branch or this branch. So what does that tell me I need to do to those 2 numbers? Add them together, which is going to give me 30 over 64. And can somebody give me that rounded to 4 decimal places? 4.686. There you go. How easy is life? Yeah? Okay. You remember doing these, hopefully? Selected 2 of the same color. Doesn't select a yellow. Right? So you're just going to go through and answer those questions. Now, if we repeated it 200 times without eating any, how many times would you expect to get 2 yellow lollies? What does that mean? Expected number. So take the probability of 2 yellows times what? 200. Right? Remember, expected number. Okay? All right. Here's one that has the same number of things. I'm looking to see if there's any that don't have going all the way to the end. 6 and not 6. Okay. Now, this one brings up something interesting. The getting a 6 is 1 out of 6. Getting a not 6 is anything else. So what? 5 out of 6. Right? So not something means everything else. It's called the complement. Okay. Pretty straightforward. All right, here they're using percents. Now you could fill out a chart using percents, but can you multiply or add with percents? No, you need to change it to decimals, and then you could do those. And percents always change nicely into decimals because that's how percents are born. Okay? If one of them is 80%, what's the other one? Straight across from it. 20, because 100% is 1. Okay? All right? So there shouldn't be anything on here that's two out there, but you're going to want to get used to working with them. Your biggest job, and the one that you're going to hate the most, is writing the probability statement and then doing the math at the end. Okay? I know you don't like to do this part of it. Tough. You will do that part of it, or your question will be wrong. So be careful. I don't grade these and I don't make the rules. That's just the way it is on NCEA on these particular things. Okay? There you go. So we have some work. Let's say we started where? Page 19. So any of these from 19 through page 25. There you go.